Welcome! In this session, we'll explore an essential problem in computer science, problem number 300, longest increasing subsequence. We'll break down the concepts, discuss multiple approaches, and focus on the recursive backtracking method. Let's dive in. The longest increasing subsequence problem challenges us to find the length of the longest subsequence in a given array of integers where all the elements are in strictly increasing order. A subsequence is a sequence derived from the original array by deleting some or no elements, but the relative order of the remaining elements must stay the same. For instance, in the array nums equals 10, 9, 2, 5, 3, 7, 101, 18, we want to identify the longest sequence of numbers that are arranged in strictly increasing order. The task is to return the length of this sequence. For the input nums equals 10, 9, 2, 5, 3, 7, 101, 18, the output is 4. The reason is that the longest increasing subsequence in this case is 2, 3, 7, 101. These numbers are in strictly increasing order, and the length of this subsequence is 4. Another example is nums equals 0, 1, 0, 3, 2, 3. Here, the output is also 4, as the longest subsequence is 0, 1, 2, 3. Notice that while there may be other subsequences, we are specifically looking for the one with the maximum length that maintains the increasing order. Now consider the input nums equals 7, 7, 7, 7, 7, 7, 7. In this case, the output is 1. Since all the elements are the same, no strictly increasing order can be formed. Therefore, the longest increasing subsequence contains just one element, 7, and its length is 1. The constraints for this problem specify that the length of the array can go up to 2500, and the values in the array can range from -10⁻4 to 10⁻4. This means that our solution must handle both large input sizes and wide ranges of values efficiently. Some key edge cases to consider include arrays with only one element. For example, if nums equals 1, the output is simply 1, as the array itself is the longest subsequence. Another case is when all elements are in strictly decreasing order, such as nums equals 5, 4, 3, 2, 1. Here, the output is also 1, as no element is greater than the one before it. Similarly, if all elements are equal, like nums equals 7, 7, 7, 7, the output remains 1, since increasing order cannot be achieved. These examples highlight the importance of handling edge cases in the solution. To begin, let's consider the brute force approach using recursive backtracking. The idea here is to explore all possible subsequences of the given array and check which ones are strictly increasing. By generating all subsequences, we ensure that no potential solution is missed. We can achieve this by using recursion to build subsequences incrementally, starting from each element. However, this method comes with a significant drawback: its time complexity is exponential, specifically O(2 to the power of n, because each element has two choices either to be included or excluded. Additionally, it requires O(n) space to handle the recursion stack. While this approach is simple to implement and guarantees correctness, it quickly becomes impractical for arrays with more than a few elements due to its inefficiency. This trade-off makes it unsuitable for larger input sizes, but it's a good starting point to understand the problem structure. A more efficient solution is the dynamic programming approach with a time complexity of O(n squared). Here, we use a DP array where DP, I, represents the length of the longest increasing subsequence ending at index I. For each index I, we look at all previous indices j where j is less than I. If nums, j, is less than nums, I, it indicates that the current element nums, I, can extend the subsequence ending at nums, j. In that case, we update dp, I, as the maximum of its current value in dp, j, plus 1. Finally, the result is simply the maximum value in the dp array, which represents the length of the longest increasing subsequence in the array. This approach efficiently breaks the problem into smaller subproblems, leveraging the relationship between indices to build the solution incrementally. While it is significantly faster than brute force, the nested loop structure still makes it less suitable for very large arrays. The most optimized solution uses a binary search approach, achieving a time complexity of O(n log n). This method employs a greedy strategy combined with binary search. We maintain an array called sub, where sub I represents the smallest possible ending value of an increasing subsequence of length I plus 1. For each element in the input array, we use binary search to determine its position in the subarray. If the element can extend the current subsequence, we append it to sub. Otherwise, we replace the existing value at the found position, ensuring that sub always contains the smallest possible values for subsequences of different lengths. The key insight here is that we don't need to store all LAS values, tracking only the minimal representation suffices. This dramatically reduces computation time while maintaining correctness. However, this approach only provides the length of the LIS and not the actual subsequence, which could require additional bookkeeping. Given these approaches, we chose the binary search strategy for its optimal time complexity of n log n, making it the best fit for large input sizes, even up to 10 to the power of 4 elements. This method effectively balances efficiency and simplicity, leveraging the greedy approach in binary search to minimize unnecessary calculations. The dynamic programming approach is still a viable choice for smaller input sizes or when the actual subsequence is required, as it directly constructs the LIS. However, for larger arrays, its n squared complexity makes it less competitive. The brute force method was ruled out entirely due to its exponential time complexity, which is impractical for all but the smallest input sizes. One of the key insights was that the LIS problem can be solved incrementally, and the breakthrough came with realizing that we only need the smallest possible values for subsequences. This observation enabled the use of binary search to achieve superior efficiency with the greedy strategy. The binary search approach stands out as the most efficient solution for this problem. It avoids the nested loop structure of dynamic programming, making it significantly faster for large inputs while remaining straightforward to implement. Although it does not directly reconstruct the subsequence, the problem only requires the length, so this trade-off is acceptable. The final solution effectively balances computational complexity and performance, making it ideal for competitive programming and real-world scenarios where input sizes can be substantial. By leveraging the minimal representation of LIS information in binary search for fast updates, this approach achieves the best combination of speed and simplicity, ensuring it meets the problem's requirements efficiently. The problem asks us to find the length of the longest increasing subsequence, or LIS, in a given array of integers. A subsequence is any sequence derived from the array by removing some elements, or none at all, while maintaining the order of the remaining elements. The brute force approach to solve this problem involves recursive backtracking. Here, we explore all possible subsequences, check which ones are strictly increasing, and return the length of the longest subsequence found. To implement this, we define a recursive function, findLIS, which takes two parameters, index, representing the current position in the array, and previous, the value of the previous element in the subsequence. At every step, there are two choices. We can either include the current element in the subsequence if it's greater than previous, or we can skip the current element and move to the next one. These choices form the basis of our recursive exploration. The algorithm terminates when index equals the length of the array, as there are no elements left to process. In this base case, we return 0. For the recursive case, the function evaluates both possible decisions, including the current element, if it satisfies the condition, or excluding it. The result is the maximum of the two outcomes. To get the final result, we initiate recursion from index equals 0 and set previous to a very small value, such as -infinity, to indicate that no element has been added to the subsequence yet. There are some edge cases to consider. If the array is empty, the LIS length is 0. And if all elements in the array are identical, the LIS length is simply 1, as only one element can be taken. While this brute force approach is conceptually simple, it's computationally expensive. The time complexity is 2 to the power of n, because every subsequence is explored, and the same index in previous combinations are often recomputed multiple times. To address the inefficiency caused by redundant computations, we can use memoization or dynamic programming to optimize the solution. In terms of data structures, the brute force method doesn't require additional storage apart from the recursive call stack. The recursion depth is proportional to the length of the array, so the space complexity is n. Let's consider a specific example to understand the steps involved. If the input array is 3, 10, 2, 1, 20, we start at index 0 with previous set to -infinity. The algorithm explores both decisions, including the element 3 and excluding it. If included, we recurse with previous updated to 3 and move to index 1. Similarly, for each subsequent element, the algorithm evaluates both options. Ultimately, the LIS for this array is 3, 10, 20, and the length is 3. The two key decisions at each step are the include and exclude choices. When including an element, we check if its value is greater than previous. If so, it becomes part of the subsequence, and we move to the next index with previous updated to this value. Alternatively, we can exclude the element, keeping previous unchanged and moving to the next index. After exploring both decisions, we combine the results using the max function to determine which path yields a longer subsequence. However, the brute force approach has exponential time complexity, 2 to the power of n, due to the sheer number of subsequences explored. The space complexity remains n, because of the recursive stack. To visualize this process, consider the recursive tree generated for the input 3, 10, 2, 1, 20. At the root, we start with index equals 0 and previously equals infinity. From there, the tree branches out as each element is either included or excluded, creating an exponentially growing structure. This recursive tree demonstrates the inefficiency of the brute force approach. For every element, the algorithm explores two possible paths, either including or excluding the element, leading to an exponential growth in the number of recursive calls. As the array length increases, this approach quickly becomes impractical due to the sheer number of combinations it needs to evaluate. While the brute force method is a good starting point for understanding the problem, it highlights the need for optimization through techniques like memoization or dynamic programming, which we'll explore later to make the solution more efficient. This code solves the longest increasing subsequence problem using a dynamic programming approach. Let's break it down step by step. 1. Edge case check. The function first checks if the input list nums is empty. If it is, the function directly returns 0, as there is no subsequence to consider. 2. Dynamic programming initialization. An array DP of the same length as nums is initialized with all elements set to 1. Here, DP I represents the length of the longest increasing subsequence that ends with nums I. Each element starts at 1, as the minimum length of any subsequence is the element itself. 3. Nested loops. The outer loop iterates through each element in nums, starting from the second element, and the inner loop checks all previous elements. If a previous element nums j is less than the current element nums I, it means nums j can be part of the subsequence ending at nums I. In this case, the length of the subsequence ending at nums I is updated to the maximum of its current value, dp I, and the length of the subsequence ending at nums j plus 1 dp j plus 1. For result calculation, after processing all elements, the maximum value in the dp array is returned as the length of the longest increasing subsequence. This works because the dp array contains the LIS lengths for all possible ending points in the array. Complexity analysis. Time complexity. The solution has a time complexity of n squared, where n is the length of nums. This is due to the nested loops iterating over all pairs of elements. Space complexity. The space complexity is n for the DP array. This implementation is efficient and handles edge cases like an empty input list gracefully. It ensures that the problem constraints are satisfied and provides the optimal solution. Here, we begin by creating a method called length of LIS that takes an array of integers as input. The goal is to determine the length of the longest increasing subsequence in this array. We first handle edge cases by returning 0 if the array is null or empty. Then, we define a dynamic programming array, dp, where each element represents the length of the longest increasing subsequence ending at that index. Initially, every element in dp is set to 1, since each number on its own is a subsequence of length 1. Next, we use a nested loop to iterate through the array. For each element at index I, we check all previous elements at index j. If the value at nums j is less than nums I, it means that nums j can be included in the subsequence ending at nums I. In this case, we update dp I to be the maximum of its current value, or dp j plus 1, effectively extending the subsequence. After populating the dp array, the next step is to determine the maximum length of any increasing subsequence in the array. To do this, we iterate through the DP array and track the maximum value in a variable called maxLength. Finally, we return maxLength as the result, which represents the length of the longest increasing subsequence. This approach ensures that we evaluate all possible subsequences and find the optimal solution efficiently, leveraging dynamic programming to optimize our calculations. We start with the example where nums is 10, 9, 2, 5, 3, 7, 101, 18. To solve this, we use dynamic programming. First, we initialize a DP array of the same length as nums, where each element is set to 1. This is because the shortest increasing subsequence ending at any index is the element itself. Next, we begin iterating through nums using an outer loop. At I equals 1, we compare nums 0 and nums 1. Since 10 is greater than 9, we don't update the DP array. It remains 1, 1, 1, 1, 1, 1, 1, 1. Then, for I equals 2, we compare nums 2 with nums 0 and nums 1. Again, since both 10 and 9 are greater than 2, no updates are made to DP, which still stays as 1, 1, 1, 1, 1, 1, 1, 1. This initialization highlights how we systematically build the DP array step by step by comparing each element with all previous elements. Now for I equals 3, we begin comparing nums 3, which is 5, with previous elements. Comparing nums 2 and nums 3, we see that 2 is less than 5, so we extend the subsequence ending at index 2 to include nums 3. This updates DP 3 to 2, resulting in DP equals 1, 1, 1, 2, 1, 1, 1, 1. Continuing this process for the remaining indices, we update the DP array whenever we find a valid subsequence. After processing all indices, the final DP array becomes 1, 1, 1, 2, 2, 3, 4, 4. The length of the longest increasing subsequence is the maximum value in DP, which is 4. Moving to another example, nums equals 3, 4, 5, 1, we initialize DP as 1, 1, 1, 1. For I equals 1, comparing nums 1 and nums 0, we find that 3 less than 4, so we update DP 1 to 2, resulting in DP equals 1, 2, 1, 1. Next, for I equals 2, we compare nums 2, which is 5, with previous elements. Both 3 and 4 are smaller than 5, so we extend the subsequences ending at those indices to include 5. This updates DP 2 to 3, resulting in DP equals 1, 2, 3, 1. For I equals 3, we compare nums 3, which is 1, with all previous elements. Since 1 is smaller than all of them, no updates are made to DP, which remains 1, 2, 3, 1. The maximum value in DP is 3, which gives us the length of the longest increasing subsequence. Finally, let's consider nums equals 1, 3, 6, 7, 9, 4, 10, 5, 6. After processing all indices, the DP array becomes 1, 2, 3, 4, 5, 3, 6, 4, 5. The length of the longest increasing subsequence here is the maximum value in DP, which is 6. The key insight from this approach is that DP, I, represents the length of the longest increasing subsequence ending at nums, I. Whenever nums, j, is less than nums, I, it means we can extend the subsequence ending at index j to include nums, I. To determine the overall length of the longest increasing subsequence, we simply take the maximum value from the DP array after processing all elements. This systematic approach ensures that we capture the longest increasing subsequence efficiently while iterating through the array. To determine the time complexity of the dynamic programming solution for finding the longest increasing subsequence, let's break it down step by step. First, we have the outer loop, which iterates over each index of the input array nums. If the size of the array is n, this loop runs n1 times, contributing O(n) to the overall complexity. Then, within the outer loop, there's an inner loop that processes all indices before the current index. For a given index I, the inner loop runs I times. This means that as I increases, the iterations accumulate, resulting in a total of 1 plus 2 plus 3 plus n1 operations. This summation simplifies to n1 asterisk n/2, which is n superscript 2. Finally, within the inner loop, there's a constant time comparison and a max operation, each taking O(1). These operations have negligible impact compared to the nested loops. Altogether, the dominant factor in the time complexity is O, n superscript 2, which comes from the nested loop structure. Combining everything, the overall time complexity of the solution is O, n superscript 2, in the worst case, due to the nested loops. Now, let's discuss the space complexity. The solution uses a dynamic programming array DP to store the length of the LIS ending at each index. Since the size of this array is proportional to the size of the input array nums, it requires O, n, space. Additionally, the algorithm uses a few variables for iteration, such as I and j, which take constant space, or O1. Thus, the total space complexity of the solution is O, n, determined by the DP array, since the constant space usage is insignificant in comparison. Now, let's analyze the time complexity under different scenarios. In the best-case scenario, where the input array is already sorted in increasing order, every number naturally extends the previous LIS. Although the inner condition nums, j, nums, I, is always true, the algorithm still performs all iterations of the nested loops, so the time complexity remains O, n superscript 2. In the average case, the structure of the input array might vary, but the nested loops still execute in the same way, leading to O, n superscript 2, time complexity. In the worst case, where the array is sorted in decreasing order, each number forms an LIS of length 1. Even in this scenario, the nested loops fully execute, and the time complexity is still O, n superscript 2. Therefore, regardless of the input, the time complexity remains consistent at O, n superscript 2. To better appreciate the efficiency of the dynamic programming approach, let's compare it with a brute force method. A brute force solution would involve generating all possible subsequences of the input array and checking whether each subsequence is strictly increasing. For an array of size n, there are 2 to the power of n possible subsequences, making the time complexity exponential at O, 2 to the power of n. In contrast, the dynamic programming solution leverages the properties of overlapping subproblems and optimal substructure to drastically reduce the time complexity to O, n superscript 2. To summarize, the O, n superscript 2, time complexity of the dynamic programming solution arises from summing the first n1 integers, as the inner loop runs progressively more iterations for increasing values of I. The space complexity of O, n, is due to the DP array, which scales linearly with the input size. This makes the dynamic programming approach far more efficient and practical for solving the problem. When tackling the longest increasing subsequence problem, there are a few common mistakes to watch out for. First, it's important to understand that the problem requires a strictly increasing subsequence. This means that every element in the sequence must be greater than the one before it. Including subsequences where elements are equal violates this rule and results in incorrect answers. Additionally, many candidates overlook critical edge cases, like empty arrays or arrays with just one element. These scenarios often lead to runtime errors or unexpected outputs if not properly handled. For example, an empty array should return 0, and a single element array should return 1. Finally, some opt for a brute force recursive approach but fail to optimize it with memoization. This leads to an exponential time complexity of O, 2 to the power of n, which is impractical for larger inputs. Using memoization here can significantly improve efficiency and is key to solving the problem effectively. Another common pitfall arises in the dynamic programming approach. When updating the DP array, candidates sometimes forget to compare the current element with all previous elements. This oversight can cause valid subsequences to be missed, resulting in an underestimated length for the longest subsequence. Similarly, the binary search approach, while more efficient, is often misunderstood. The helper array used in this method tracks the smallest possible tail values for subsequences. Mismanaging this array or updating the wrong indices can break the algorithm's correctness. Both of these issues highlight the importance of carefully implementing and debugging your chosen approach to avoid these common errors. Now, let's talk about some broader insights and strategies for this problem. Recognizing that this is part of the longest subsequence family of problems can help you identify the right approaches. Typically, you'll choose between dynamic programming and binary search. The dynamic programming solution, with its O, n squared, time complexity, is straightforward to implement and explain, making it a good option for smaller inputs or during interviews. On the other hand, the binary search approach, which runs in O and log n, is more efficient but requires a stronger grasp of binary search and greedy algorithms. When testing your solution, always include edge cases. For instance, an empty array should output 0, a single element array should output 1, a fully sorted array should return its length, and a fully decreasing array should return 1. Lastly, this problem is closely related to others like number of longest increasing subsequences, Russian doll envelopes, and wiggle subsequence, so understanding the core techniques here will help you in similar challenges. Finally, let's compare some alternative approaches and their trade-offs. The dynamic programming approach operates with a time complexity of O n squared. It uses a DP array where each element represents the length of the longest increasing subsequence ending at that index. This method is simple to implement and works well for small to medium-sized inputs, but it becomes inefficient as the input size grows. The greedy approach combined with binary search improves this to O n log n by maintaining a helper array, where each value represents the smallest possible tail for increasing subsequences of different lengths. This is ideal for larger inputs but is harder to implement and explain, especially during interviews. Lastly, there's recursive backtracking with memoization, which explores all subsequences but caches results to avoid redundant calculations. While this approach can be intuitive for those comfortable with recursion, it's less efficient than binary search and risks stack overflow with large inputs. Each method has its strengths and weaknesses, so choosing the right one depends on the context and constraints of the problem. Great work! To sum up, we covered the brute force approach for the longest increasing subsequence problem. While not the most efficient, it's a great starting point for understanding the problem and building toward optimized solutions. Thank you for joining, and be sure to stay tuned for more coding tips and tricks. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!